In this presentation, we will show some typical applications of low-energy ion scattering with regards to thin film analysis. For thin film applications of up to a few nanometers of thickness, LEIS delivers two kinds of information. Firstly, the quantitative elemental composition of the outermost atomic layer, and secondly, the in-depth signal of heavier elements of the first few nanometers of the sample without sputtering. Why LEIS is quantitative for the outer atomic layer and how the quantification works is explained in a separate video. There is also a video on the details of the static in-depth signal, so we will not go into too much detail here. First example of spectra from a thin film sample set very nicely illustrates the basic components in a LEIS spectrum. The peaks correspond to the composition of the outermost atomic layer. The ions leading to these peaks have been scattered at a surface atom and underwent an energy loss that is characteristic of the mass of the surface atom. The tails to the left of the zirconium peak correspond to ions which have been scattered at zirconium atoms below the surface. As these ions have to travel through the solid, they undergo an additional energy loss, so they appear in the spectrum at lower energies than the ions scattered at the surface. This energy loss is proportional to depth. Also, the intensity is smaller, making it possible to distinguish the signal of the outer atomic layer from that of deeper layers. This sample set consists of zirconium oxide films grown by ALD on silicon oxide. The number of ALD deposition cycles corresponds to the amount of material deposited. With increasing number of cycles, the surface peak of zirconium, representative for zirconium oxide, increases, while the silicon peak decreases. This means the surface area covered by zirconium oxide is growing, but even after 70 cycles, less than 100% of the surface is covered by zirconium oxide. Only after 100 cycles is the silicon peak completely gone. A tail to the left of the zirconium peak develops with increasing number of deposition cycles, indicative of the depth distribution of zirconium. This indicates that prior to the formation of a closed film, part of the material is growing in multilayers. If we look at the blue spectrum, 40 cycles, we see about 50% surface coverage from the intensity of the surface peak. At the same time, we see a tail which extends more than 200 eV to lower energies, corresponding to more than 1.5 nanometers of thickness. This means that while about 50% of the surface is still not covered, part of the covered area is up to 1.5 nanometers thick. In this way, the growth mode in the deposition process can be determined. In this example, palladium deposition on zinc oxide is studied in the context of a new process for ALD. This process is aimed at palladium deposition on heat-sensitive materials, allowing only for low process temperatures. One idea was to add a third phase in the ALD cycle by dosing TMA to increase the growth rate of palladium. TMA is a typical ALD precursor for aluminum oxide, but the aim was to suppress the aluminum growth because of the low temperature. The LEIS data still shows, besides the fluorine contamination from the precursors, that a low growth rate for palladium. The peak is detected but not very intense. Specifically, it is only weakly increasing with the number of deposition cycles. While at 0 cycles, the zinc from the zinc oxide substrate is clearly detected, it is already completely covered after 25 cycles. As palladium is only seen with low intensity, the simultaneously appearing aluminum must be the dominating compound in the film. In the 25 cycle spectrum, the in-depth signal of zinc below the surface is still visible. At 50 cycles, the in-depth signal is already fully overlapping with the low mass peaks. To better visualize the in-depth signal, 7 keV helium scattering was used. At the higher energy, the surface peaks get less intense compared to the in-depth signal. We are starting to leave the LEIS energy regime and moving towards MICE, or medium energy ion scattering. The spacing of the surface peaks on the energy scale is proportional to the primary energy, while the width of the in-depth signal is much less than proportional. This means that a larger depth range can be fitted between the surface peaks. Under these conditions, the zinc in-depth signal for 25, 50 and 100 cycles can be clearly identified. In order to quantify the palladium coverage, increasing with the number of deposition cycles, 5 keV neon scattering was applied. This reduces the background and improves sensitivity and mass resolution for heavier elements. By comparison to a palladium reference, the palladium surface fraction can be quantified for each sample and plotted as a function of the number of cycles. It reaches a maximum of 4.5% as the palladium growth is in competition with a much more efficient aluminum oxide growth. This example of a complex ALD film is from the field of optoelectronic materials. Mixed gallium antimony films were grown from 0 to 100 cycles and analyzed using 3 kV helium scattering. It is obvious that no unexpected elements were detected and the gallium and antimony peaks are separated, but the in-depth signals overlap, making quantification difficult. Using 7 kV helium scattering, the surface peaks are more spaced, allowing for the in-depth signal to be separated, at least for gallium, and for part of the antimony peaks. Also, the peaks are less intense. In this way, a growth curve in angstroms per cycle can be determined. By switching to 5 kV neon scattering, the peaks of gallium and antimony become nicely separated and easy to evaluate. By including the silicon peak from the 3 kV helium scattering spectra, the surface composition was quantified and is shown in the lower plot. The silicon substrate signal disappears for increasing number of cycles and practically reaches 0% at 20 cycles. The other two elements are more interesting. The antimony coverage picks up much quicker than the gallium coverage until it reaches about 60%. The antimony coverage then drops to about 45% and stays there while gallium continues to rise to about 55%. The interpretation is as follows. Antimony growth is favored on the silicon oxide substrate, so it starts quickly. Gallium grows well on both gallium and antimony, so its growth is slower while silicon oxide dominates the surface. Gallium reaches a high level while antimony drops again when no silicon oxide is available anymore. Once an equilibrium is found, the ratio of the two metals stay constant. It is important to realize that this can be viewed as a depth profile of the complete 100 cycle film, from the interface to the surface of the film. The 100 cycle sample has gone through all these concentration changes, which are most dynamic close to the substrate, before the film is closed. However, a sputter depth profile, for example using SIMS, will not be able to quantify the large changes in the matrix composition close to the interface, as the SIMS matrix effects are very strong. Other techniques are not capable to deliver sufficient depth resolution to resolve these changes. The final example of this video is from molybdenum silicon multilayer films. These are used as X-ray mirrors for current EUV lithography tools. To reach optimum reflectivity, diffusion barriers were developed to increase interface stability, and these were studied using LEIS. A model system of 5 nanometers silicon on top of 10 nanometers molybdenum was deposited, separated for example by a thin B4C diffusion barrier. The LEIS spectrum of the sample as deposited, the black spectrum, shows no molybdenum surface peak, only silicon and oxygen. To the right of the silicon peak, the in-depth signal of the buried molybdenum layer is visible. Heating the sample in the analysis position to 660 degrees C and taking spectrum makes the diffusion of the molybdenum visible. The in-depth signal is moving towards higher energies as the interface is moving towards the surface. After about 1 hour of heating, a molybdenum surface peak appears and the in-depth signal to the left of the surface peak becomes horizontal. This spectrum is practically identical to a MOSI-2 reference spectrum showing the formation of a silicide. By performing the same experiment at a lower temperature, 500 degrees C, the process is slowed down and can be carefully watched. The change in the spectra can be described by the diffusion formula, so the diffusion coefficient of the different diffusion barriers can be extracted. This was possible without any sputtering and by a single experiment, just taking the time for the diffusion itself. To summarize, LEIS is very well suited to study thin films from submonolayers to several nanometers of thickness. It yields information about layer closure, growth modes, and thickness evolution, and can be applied to complex films. Diffusion can be studied in real time without any sputtering. For more information, please visit iontoff.com/QTAC.